Not today. We'll be mostly doing lectures today, so no MATLAB today. Yeah, Wednesday we'll do MATLAB stuff.
How's it going, Dr. Tran? How's it working?
Dr. Tran, can I ask a question real quick before
Sure.
class?
Yeah, what's up?
If I have two springs, like in problem 1, so if I have two springs attached to the same board,
Yep.
do I just multiply it by 2? That's it?
Yeah.
Okay.
Specifically, there's two. They each have their own element stiffness matrix, but since they interact with the same nodes, so they just overlap, and so you end up multiplying it by 2.
Okay. So the value inside the stiffness matrix is multiplied by 2.
Exactly.
And then if it overlaps with another spring, but not attached to the same board, you just add it to the times 2. Okay.
Exactly.
All right.
Yep.
Thanks, Dr.
Yep. Mm-hmm. I tried Lost Ark. I did. All my friends are playing it.
Yeah, sorry,
The issue I have, I picked the artillery one, the one with the big gun. The issue I have with MMOs is that I always end up falling behind my friends. So all my friends are like level 40 or something already, and I've only played like for an hour, and I'm still like level 12 or something.
Yeah, same.
But it's fun. It's very polished. It's a fun game. I'm already in a guild with my friends.
I was just like curious.
Yeah. I watched a Super Bowl with some friends yesterday. I was telling Dr. Wang that I was just here that I'm kind of running on fumes right now because yesterday the game was pretty exciting, and so we only just had snacks, and so there was before lunch today I had only eaten just chips and gummy worms for like over 24 hours, and so I woke up today feeling like crap, and then I feel a little bit better after lunch, but still a little bit tired.
Yeah, that'll do it.
Yeah, my body's getting old. I can't eat junk food and still feel good after that anymore.
Yeah, it was a good game though.
All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Good. Happy Valentine's Day. You have a great Valentine's Day planned for this evening. You get to spend it with me in this class. So that's fun. Yeah, me and my wife, we can't do anything either because she works late, I work late, so we're probably gonna do something another time. Okay, so the plan for today is we're gonna be starting a new set of lecture notes, and today we're gonna be venturing into the realm of 2D solutions. And so for me, I think this is a really exciting week because I think last week was kind of our first foray into what this class is all about, which is just using finite differences and Matlab to solve differential equations. Last week, we kind of got our toes wet a little bit, where we solved some 1D problems, which was fine. It was fun, but a lot of those problems we could just solve just by hand. And so this week we're going to start getting into the realm of these are problems that are normally really hard to do by hand, or that you wouldn't ever want to do it by hand. But with MATLAB, you'll see that it's a lot easier, and you could produce plots that are really pretty too. And so a lot of the characteristic plots for this class, the ones I use for a lot of the show and tells, come from this unit. Okay. But with that said, this week is going to be one of those weeks where we kind of take a big leap. And so a lot of what we're going to cover this week has less to do with heat transfer, has less to do with computations, but more to do with kind of like just programming logic and bookkeeping and keeping organized. And so traditionally, this is the third time I've taught this class, and the last two times I've taught it, this is kind of the week where things kind of take a big leap, and then and it starts to get a little bit more challenging because a lot of what we're going to cover this week is kind of like abstract algorithms of how we kind of represent things, and just how we keep organized. Because once we start getting into 2D space, the biggest issue that we're going to have is just keeping organized with everything and making sure that we're referring to the right locations on the grid. Okay. So I think it's a really exciting week, but it also is going to be a jump. So I just want to make you guys aware of that. All right, and so I think that's all my announcements. And so are there any questions I can answer before we get started? Okay, All right, so let's go ahead and get started with 2D diffusion with finite differences. All right. And so, just like I mentioned, last week we spent the whole week talking about 1D problems, right? So we solved for 1D ODEs with their 1D solutions, and all of that was great. Okay. And so kind of the next step for this class, and another step towards eventually what a lot of these techniques are used for, is to move to the second dimension. Okay. The interesting thing with adding the second dimension is that conceptually, nothing's really going to change, and so we're still going to take our equation and we're still going to discretize it with finite elements. Okay. The main thing that's going to change is how we actually write the program and how we keep all the information organized. Okay. Because what you'll see is that a lot of the the data structures and a lot of the organization that we did for 1D, a lot of that was kind of implicit. It was kind of obvious, just kind of based on the simplicity of the domain. But now that we're in 2D, we're gonna have to start thinking about, how do we actually refer to the nodes? How do we actually, relate them to each other? And how do we form our system of equations? So now it's not going to be as trivial. Okay. All right. So with that said, let me go ahead and write out the equations that we're going to solve. Okay. Okay. And so our 2D diffusion equation consists of two derivatives. Okay. So we have one derivative with respect to x, and so that's our second order derivative. Then we have a second order derivative with respect to y. Okay. And so those are added to each other. And then on the other side of the equal sign, we have a source term. Okay. Okay. So conceptually, very similar to our 1D equation. It's just that we added another derivative there. Okay. And so this type of equation right here, this is called a Poisson equation. So Poisson equation is nothing more than just a diffusion term or diffusion terms along with a source term on the right. Okay. Another form of these equations that we'll work with first, just for the sake of simplicity, is known as the Laplace equation. And the difference between Laplace and Poisson is that we're just going to set the source equal to 0. Okay. And this right here is the Laplace equation. Okay. All right. And so that's that's kind of where we're starting with. Okay. And intuitively, all we're going to do here is that we're going to take these derivatives and just discretize them with finite elements. And so the exact same thing we did in 1D. Okay. And so that part's not going to change. It might get a little bit more complicated because now we have two derivatives. But it's that's not going to be the focus of this week, because we did that all last week. The focus of this week is how do we take our 2D domain and how do we discretize it and organize it in a way that will allow us to apply finite differences. Okay. And so we're going to focus on discretizing 2D domains, 2D grids. Okay. Okay. All right. And so just like we did in our 1D case, our first step is going to be to take our problem domain and discretize it into a discrete number of grid points. Okay. And so to kind of remind you what this looks like in 1D. So in 1D, we had, our domain was simply a line. Okay? And when we discretized it, okay, all we did was we took that line and we broke it up into a bunch of smaller lines. Okay. Right. And then what we usually do is that we take each of the nodes and we just label them by their numbers. Right. Okay. And so this is how we discretize the domain in 1D. So it was very straightforward. We just took a line and broke it up, and then each of the breakpoints, each of the nodes, we just assigned an ID number to them. Okay. In 2D, it's a bit more complicated. Okay. So in 2D, first of all, there's a lot more 2D shapes than there are 1D shapes. There's literally only one 1D shape, which is a line. Okay. But in 2D, there's all different kinds of things you can do. And so the one that we'll work with the most, just because it's simple, is a rectangular domain. Okay. And if we were to discretize it, it would look something like this. Okay. Okay. So it's almost like you're putting graph paper on top of the domain. Okay. So this would be our 2D domain. This would be our 2D grid. But we're not just limited to rectangles anymore. And so we can do a lot more different shapes. And so you can imagine, we might have something like an L, right? Right, we can discretize this, something like this, right? Okay, right, that's another domain that we can do. We can do a U, right? Right, we discretize this, it might look something like this. Right. The possibilities are endless, right? And so in 2D, there's just a lot more creative things you can do with the domain. Okay. But again, for this class and for a lot of the development of the theory that we're going to be doing in the lectures, at least, we're just going to focus on just the rectangular domain, just because it's the easiest one. Okay. Okay. Any questions on this? All right, question. So can we do a heart too, or would it be strictly need to be more of a shape that can be broken down into boxes? You can do a heart. Because you can take a heart, something with curved surfaces, and at least for finite differences, the only thing you just need is our grid points. Okay, and so if you take a heart, okay, very fitting because it's Valentine's Day, I guess. Okay. The main difficulty that you would run into with a heart is a lot of our techniques here kind of rely on the distancing between the different grid points. And so if you have a node here that's connected by a curved part, you kind of run into the issues like, does that count as a neighbor or not? And then what's the distance in between those ones? And so, but a lot of this stuff is fairly automated too. And so, we're not going to talk a lot about grid generation or mesh generation because there's a lot of great algorithms for that out there. But it would do something like this. And break it. Okay. Broken heart. Okay. And so for curved surfaces like this, you can do it. And of course you have to, because there's a lot of practical situations out there with curved surfaces. But doing it with straight edges just makes the math a bit easier. Okay. All right, question. So if it's curved, would we need to use polar instead of rectangular? You could use polar coordinates, but even for curved surfaces, it's still a lot easier to use rectangular coordinates. Yeah. And so one thing that you'll see actually is, if you have a curved surface like this, they might approximate it with straight line segments. Okay. And so that's kind of traditionally what you'll see. Mhm. All right, any other questions on 2D domains? Okay, all right. And so, when we do break up a 2D domain like this into a 2D grid, the thing I'm going to emphasize the most and the thing that's most important going forward is that we stay organized, okay? Because what you'll notice here is that now that we're in 2 dimensions, there are a lot more parameters and a lot more variables to keep track of, okay? Okay. Right, and so for 2D problems, we're really going to make use of the power of programming to save a lot of this information in variables. Okay, we're going to save a lot of these in variables and then call upon them later in the program to actually execute our algorithms. Okay. All right, so let's look at the really basic stuff first. And so let's look at a general kind of 2-dimensional domain, or 2D grid, I should say. Okay. Right, and so the first 2 things that we can parameterize is the length of the domains in each direction. Okay. And so we have Lx. Okay, so Lx is the horizontal length of the domain. Okay, then we have Ly. Ly here is, of course, the vertical length of the domain. Okay, and so those are 2 good quantities for you to save in variables when you're writing your programs. Then we have Nx, and so Nx here will be the number of grid points in the horizontal direction. Okay. And so if you travel a horizontal line at any point in this grid, if you count the number of nodes that you cross over, that's going to be Nx, right? And so for this particular problem, if we go, let's use the bottom edge as an example. Okay, that is not what I want. Okay. And so we follow the bottom edge. You can see here that we have 1, 2, 3, 4, 5, right? And so for this particular problem, or for this particular domain, Nx is 5 because we have five nodes in that direction. Okay. And if we have Nx, then we're going to have Ny. And so Ny is the number of nodes in the vertical direction. Okay. And so to obtain this, we just walk up a vertical line and we count how many grid points that we see. Okay. So in this case, it might be actually even. So let's count on this one. We have 1, 2, 3, 4, 5, 6. Oh, it's uneven. Okay. And so in this case, we have six grid points in that direction. Okay. And so all of these are quantities that you should be aware of in your problem, and you should assign variables so that you can call upon these later on in the code. Okay. All right. And so now that we know the length of the domain in each direction, and now we know the number of grid points, we can use these to compute the grid spacing. Okay. And so let's start with delta x, okay? And so delta x is the space in between grid points in the horizontal direction, right? Right, and so the way that we compute delta x, where, of course, we're going to assume that we have a perfectly uniform grid. And so the grid spacing is the same, across the entire grid. Okay? So we have Lx divided by nx minus 1, okay? And then we can have the same thing for delta y. So delta y is going to be Ly divided by ny minus 1. Okay. So does everyone remember why we minus 1 in these equations? Because remember the deltas is the grid spacing, right? And so we're not counting, and so we're not using the number of grid points in that direction. We want to count the number of grid spaces there are, right? And so let's take the x direction as an example, right? So we have nx is equal to 5, but let's count the actual number of spaces that we have. And so we have 1, 2, 3, 4 spaces, right? And so in this case, to compute the grid spacing, we take the length of the domain in that direction divided by the number of grid spaces, not the number of grid points. Okay. All right. Any questions on this? Okay. All right. And so all of these, probably if you're doing a 2D problem, this is kind of the first thing that you compute, the first thing that you store in variables. And once you have them, you can stash them away in variables and then use them. Okay. All right. So the next thing I want to talk about is a node numbering scheme, okay, or node labeling. All right, so the question in the chat, so is delta x equal delta y? It doesn't have to be. And so you can have different grid spacing in the x and the y direction. And so you can have, a certain grid spacing in x, maybe you have like 10 grid points in that direction, but maybe you need more spatial resolution in the y direction. So maybe you have 100 grid points in that direction. And so they don't necessarily have to be the same. For a lot of what we do, we are going to assume a perfectly uniform grid. And so if you do assume that, then delta x equal to delta y, but they don't have to be. And you'll see later when we discretize the diffusion equation, you can have them separate, and it works just fine in the equation. You just have to kind of keep track of that. Okay. All right. So node numbering, node labeling. Okay. So let me preface this by saying that remember that when we are doing our our finite difference method. What we end up getting is an algebraic equation for every node in the mesh. Okay. Okay. And the way that we kept track of each equation is based on the number that we assign to it in our grid. Okay. And so in other words, when we discretize our 1D equation, we broke it up into nodes. Then we know that for every single node, we're going to get an equation. And the way that we ordered those equations, the way that we organized it, is based on the numbering that we gave. In 1D, this is fairly trivial, and so we spent literally no time talking about it, right? And because it's pretty obvious that if you have a grid that if you have a line that you're going to discretize into grid points, Okay. Right. It's pretty clear that you should number it something like this, right? So you just number from left to right, 1, 2, 3, 4, 5. We're going to have 5 equations, and then those nodes are going to, when we apply finite differences, or sometimes boundary conditions to these nodes, that's what's going to give us our equations. Okay. In 2D, the numbering scheme isn't obvious, and actually there's lots of different ways that you can do it. Okay. Okay. Right. So if you grid like this, okay. One way that you can do the numbering is you can take each of the grid points. You can, or one smart way to do the numbering is to start at a certain location, and then just start numbering from there. Okay. And so if we imagine this grid to be kind of like an XY axis, where the x-axis is this way, and the y-axis is this way. Okay. Usually the place that makes the most sense to start numbering is where the origin of this of the system is. Okay. And so the origin is usually this guy right here. Okay. Right. And so this will have the our starting point. So this will be grid point number 1. Okay. But from here, you can do almost anything. And so one way that you can do is you can start going from left to right. And so you can call this one node 2, call this one node 3, this one's node 4. And then when we reach the end of the row, we just move up to the next one. Okay, so 5, 6, 7, 8, and so on and so forth. Okay. But that's not the only numbering scheme out there. And so you can actually take this and start numbering in the vertical direction first. So you go 1, 2 here, 3, 4, and so on and so forth. Okay. And so there's lots of different ways you can do this. And I won't enforce a single way onto you. But for my notes, I will use the same convention throughout the notes. And so, if you want to follow along with the notes and a lot of the starter code, this is the convention that I'm going to use. Okay. And so the convention I'm going to use is I'm going to use the one that I have here, where you start going horizontally from left to right. Okay. So let me go ahead and fill in the rest of these just so we can use this in an example. And so in this case, we have 20 grid points. Okay. And so this scheme starts at the origin. And numbers from left to right. If we do that, then you can see that we hit, first of all, we hit every single node in a very systematic way, and each one is assigned a unique ID number that no other node has. Okay. All right. And so that's all well and good, right? And so that's fine. Where things get a bit complicated is how we're actually going to refer to this scheme in the code. Okay. Okay. How do we refer to the scheme in the code in a flexible way that allows us to change the grid? Okay. And so the easiest way to do things is if you have a very specific grid like this. Let's say that ahead of time. Maybe it's because I assigned you a problem or something like that. That the grid is going to be 20 points, right? And so you can just hard code the things in there. And by hard code, I mean you can just say that for this node right here, its neighbors are going to be 5, 6, or 5, 7, 2, and 10, right? So that's one way you can do it. But then your code becomes really inflexible, and you can't adjust the code for any kind of differences. Okay. And so let me add an addendum to this. And so instead of just saying how do we refer to the scheme in the code, how do we refer to this scheme in the code in a flexible and scalable way. Okay. And so for this, you kind of have to take the perspective of the computer, right? And so for the computer's sake, all as a computer is that you're going to be thrown a 2D problem at you. And so you don't know how big the grid's going to be, how many grid points there are ahead of time. And so you have no idea what that number is. Only the user knows, but you as the computer does not. Okay. And so you need to come up with kind of a surefire systematic way to refer to these nodes in a systematic way. Okay. And to help with that, let me go ahead and redraw the grid again. But instead of drawing the ID numbers, I'm going to put in the XY coordinates of each node. Okay. Specifically, I'm going to put it in terms of the number of grid points there are in those two directions. Okay. And so it's not XY coordinates. I like to call these IJ coordinates. Okay. Okay. Where I here is like an X, I call this like an X index. Okay. And J is the Y index. Okay. Right. So all the I and J's are going to do is they're going to count how many grid points we've moved over, in those respective directions to get to the location that we're at right now. Okay. Okay, so let's start at the origin. And so the origin is going to be 1, 1, okay, because that's the first node in the X direction and the first node in the Y direction. Okay. Next, we're going to have 2, 1, because we moved over 1 in the X direction. So the I value becomes 2. Okay. And if we fill out the rest of the row, it's going to be 3, 1, and then 4, 1. Okay. And if you fill the entries into the next row, then it's going to be 1, 2, 2, 2, 3, 2, 4, 2. Okay. And next row is going to be 1, 3, 2, 3, 3, 3, 4, 3. Okay. Right, and so on and so forth. Okay, so I'm not going to fill in the top 2 rows because you guys can guess what those look like. Okay. Right, so these IJ coordinates are another way to represent the 2D grid that we're looking at right here. Okay. And we're going to need both, and so both of these are going to be needed. Because from the top's perspective, right, and so where each node has a unique ID number, this is going to be useful for us when we're constructing our linear system of equations. Okay. Okay. Because remember, when we form our linear system of equations, we need one equation for each node, and so this unique numbering system will let us know which row will go for which. Okay. All right, but the IJ notation is this is going to be useful for us because our finite difference equation, our finite difference approximation, is formatted in this way. Okay. Okay. Right, and what I mean for that is, when we apply the finite difference scheme to our 2D diffusion equation, we're going to need to do things like, we're going to need to pull in our neighbor on top or our neighbor on bottom or a neighbor to the left, to the right, right? And if we're using this IJ notation, it's very easy, right? And so if we look at, we just look at any generic node, I, comma j, right? And so this could be anything. And so this could be like 3, 2, it could be 4, 3, something like that, right? If we were at a random node like this, and if let's say that we needed to poll, or we needed to get the value of all our neighbors, okay? Okay. Right, and so let's say that we need to get the value of the right neighbor. We need the value of the left neighbor. We need the value of the top neighbor and the bottom neighbor. Okay. Right. The neighbor that's immediately to the right of I, comma j, the way that we obtain that is just going to be I plus 1, comma j, right? Because in order to move to the right, we just increase our x index by 1. Okay. By that same logic, our left neighbor is going to be I minus 1, comma j. Okay. Our top neighbor, we're going to leave I alone. Instead, we're going to increment j. Okay, so our top neighbor is going to be I, comma j plus 1. Okay. And the bottom neighbor is going to be I, comma j minus 1. Okay. And so if I just give you a random node, so if I gave you the 3, 3 node, you can very easily tell me, what's the coordinates of the left neighbor, what's the coordinates of the right neighbor, what's the coordinates of the top and the bottom one, right? Because you just add 1 or subtract 1 from each of the coordinates. Okay. On the other hand, and don't cheat, and so don't look back in your notes, and I kind of covered it here. If I said, if I give you node 7 in the first scheme, tell me what the ID numbers for the top, bottom, left, and right neighbors are. Right? You could probably say that, for node 7, the left neighbor is going to be 6, the right neighbor is going to be 8. But what are the top and bottom neighbors, right? It's not immediately clear. And then if I gave you, instead of a 20 node grid, what if I gave you a 200 node grid, right? And so if we had, let's say 40 nodes in one direction and 50 nodes in the other direction, right? I guess that'd be 2000. And what about then, right? And so if I told you for node, 1157, what are the left, right, top, and bottom neighbors? It's not clear, right? Because it's, because everything has a unique number, and we don't know what the unique number above or below that is. Okay. And so our goal here is we need to reconcile both of these formats, and because they both have their places, and so we're going to need both in order to write our algorithm. But we need a way to kind of connect them so that we can kind of hop between one and the other. Okay. All right. Are there any questions about these two ways to organize the nodes and what they're used for and why we need to relate them? Okay. All right. And so we have these two representations for our grid, right? And the way that we're going to relate them is with the formula. Okay. Okay. Right, and so in other words, if we're given I and j, then we can compute the ID number. Okay, and that formula is given by the following. And of course, this assumes that I'm going to use this scheme right here, where we count horizontally first. Okay, and so this formula is going to take in I and j. So I and j are the inputs. Okay. Okay. And for this particular scheme, where I count horizontally first, it has the following formula. And so we're going to take j, which is the y index. We're going to subtract it by 1. multiplied by the number of grid points in the x direction, and then to that we're going to add I. Okay. And so this formula right here gives us a way to take our, take this ij notation right here, and then compute the unique ID number based on that. Okay. All right. And so the way to kind of interpret this is kind of just based on our numbering scheme, right? And so we kind of start in the bottom left of the grid where I and j are the lowest, and then the only time where we move up another row is when the j coordinate goes up by 1. Okay. Okay. And then based on this, you can compute the ID numbers of the left, right, top, and bottom neighbor, right? Because let's say that let's say that we're using this example here, and then let me use node 7 as a result. Okay. And so from node 7, let's compute the ID numbers of the neighboring nodes. Let's do that using this formula without looking at the picture up there. Okay. All right. And so for node 7, we know that the ij coordinates of node 7 are 3, 2. Okay. That's okay. So for node 7, we have I is equal to 3 and j is equal to 2. Okay. And so let's using that, let's check to make sure that we get 7 here as well. Okay. And so we have ID at 3, 2. Okay. And so let's go ahead and plug into this formula. So we have j minus 1. And so j here is 2 minus 1. Okay. We're going to multiply the number of nodes in the x direction, which in this case is 4, right? 1, 2, 3, 4. X is equal to 4. Okay. We're multiplied by 4. Okay. And then to that, we're going to add I, which in this case, I is 3. Okay. And so we have 2 minus 1, which is 1, multiplied by 4, which is 4, plus 3 is 7. Okay. Right. And so this formula works for node 7, right? And so, if we know that the I and j coordinates are 3 and 2, then we can use this formula to compute what its ID number is. Okay. All right. So let's compute the left neighbor. And this is where our ij notation comes in handy, because our left neighbor we know is going to subtract the I index by 1. Okay. And so for the left neighbor, instead of 3, 2, we're going to have 2, 2, right? Because the I index is less than 1. Okay. So if we do ID of 2, 2, okay, we have j is equal to 2. So we're going to multiply by that, plus 4. And then now we're going to add I in this case is 2. Okay. And so the ID number of our left neighbor is just going to be 6. Okay. And that makes sense, right? And so if we go up to the grid, okay, you can see here that we have 7 right there. Okay. And so the left neighboring node here is node 6. And so that we can just visually see that. And so that's how that works out. Okay. Let me do one more. And so let's do the bottom neighbor. And so for the bottom neighbor, I here is 3, right? Because it's the same as our node of interest. But if we're on the bottom, then our j value is going to be less than 1, okay? Or 2 minus 1, excuse me. So it's going to be 1, right? And so the ID number of 3, 1 is equal to 1 minus 1 multiplied by nx, which is 4. Plus I, excuse me, which is 3. Okay. And so we have 1 minus 1 multiplied by 4, so that just cancels out and becomes 0. And then to that, we're going to add 3. And so the ID number for our bottom neighbor is 3. Okay. And if we go back to the figure up here, right, we can see that the bottom neighbor for node 7 is indeed 3. Okay. And so this equation here holds up. Right? And so this equation is going to be really clutch for us. And so because what we're going to do basically is we're going to write loops to loop over all the nodes in the grid and then form our finite difference equations, based on the I and J coordinates. Okay. Any questions on this? Okay. All right, so a couple other pieces of housekeeping before we actually start doing finite differences. And so a few other useful parameters to know. And so first thing that would be useful is the n total, which is the total number of nodes in the system. So not just nx, not just ny. So how many nodes total that we have. And the way that we obtain that is we just take nx, we take ny, and we multiply them together, and that's how we get n total. Okay. Right. Another useful thing to remember is that even though we're solving a 2D system, in the end, we're still going to get a linear system of equations. Okay. Right, and so we're still going to end up with something like this, where we have A multiplied by X is equal to B, okay? Where A, of course, here is the left-hand side matrix, X is our solution variable, and B is the right-hand side vector, okay? Right. And to this end, combining together with our computation for n total, we can come up with formulas for the sizes of these vectors and matrices, okay? And so A, right, so A is our left-hand side matrix. Remember, the number of rows and columns in A reflect how many unknowns that we're solving for in our finite differences, okay? And so if we have the total number of nodes and total, that means that's how many equations we're going to have, okay? And so the size of A is going to be n tot by n tot, okay? That's how many rows and columns that we're going to have. Okay? X is going to be n tot by 1, okay, because it's a vector. Okay, and then same thing for B. Okay, so B is going to be n tot by 1. All right. Okay. One thing in particular I want you to remember, because I think this is the part that gets really confusing for people, is that your A, or the left-hand side matrix that you're going to be constructing, it's also kind of like a rectangular domain, right? And so, a matrix is basically like a 2D construct. Okay. One thing you always have to remember that when you're putting together the left-hand side matrix, the left-hand side matrix uses a different numbering, a different coordinate scheme than your domain. Okay. Okay. because remember the domain of your problem, which is what we've been working with above here with the i's and j's, that represents kind of the physical space or the physical domain where you want to solve your differential equation, right? That's different than the matrix that you're using to solve it. And so this matrix here, just kind of always remember what that represents. So this matrix here it only represents the system of equations, the system of algebraic equations that you're going to solve for, to find the solution, okay? And so it only represents the system of equations. It has no connection to the domain. Okay. I mean, it does have connections to the domain, but it's it's not actually the domain. Okay, and so you just kind of have to remember that. Okay. Any questions on this? All right, and so we've been talking about a lot of abstract systems and a lot of abstract kind of numbering schemes, and so let's see how this is all kind of added together. And so let's go back to our 2D diffusion equation and let's actually start applying finite differences to it. Okay. And so let's discretize. Because all we've done so far is just discretizing the domain, okay? And so the next step in the finite difference process is to actually discretize the equation itself. Okay. All right, so let me write out the equation again. And so we have partial squared phi over partial x squared plus partial squared phi over partial y squared is equal to q. And q here is a function of x and y because we're in a 2D domain, okay? And if we apply finite differences, we're going to take these derivatives here and write them in terms of their discrete forms. Okay? And so for the x derivative, we're going to have phi I minus 1 comma j minus 2 phi I comma j plus phi I plus 1 comma j. Okay. All this is over delta x squared, right? Plus the same thing for y. And so for y, since we're taking the derivative in y, instead of doing the incrementing on the I coordinates, we're going to increment on the j instead. And so this can be phi I comma j minus 1 minus 2 phi I comma j plus phi I comma j plus 1, okay, all divided by delta y squared, okay, and this is equal to q, and I'll call this qij for now, okay, because we're going to be evaluating that source term at the I and j coordinates, and so I'm just going to leave it like that. Okay. Okay. And so this is what we did in the 1D case, but in the 1D case we had just a single derivative, so now we have two. Okay. And so from here, usually the best thing to do is to simplify this equation so that you get kind of a simple recurrence relation for for all the different neighboring values. Okay. And so to that end, just to make things, just to make our life simpler, let's assume we have even grid spacing all around. Okay. And so let's assume that we have delta x is equal to delta y. Okay. And so the number of grid points and the lengths of each domain is the same in both directions. Okay. And just to make my life simple, I'm just going to make it delta. Okay. And so under that assumption, let me take this equation up here and multiply both sides by delta squared. Okay. And so if we do that, then we end up with phi I minus 1 comma j minus 2 phi I comma j plus phi I plus 1 comma j, okay, plus phi I j minus 1 minus 2 phi I comma j plus phi I comma j plus 1 is equal to qij times delta squared. Okay. And so all I did was I just multiplied the entire equation by delta squared just to get it from under the denominator. So it saves us a little bit of writing. Okay. And we can do one more thing to simplify this because we can see that both derivatives have an I comma j term. And so we can just kind of simply just combine these terms. Okay. So we do that, we get phi I minus 1 comma j plus phi I plus 1 comma j. Plus phi I comma j minus 1 plus phi I j plus 1 minus 4 times phi I comma j is equal to qij delta squared. Okay. And so this right here, you know, and we can call it general because, you know, we haven't plugged in anything specific for Q yet. This is kind of our general finite difference equation for 2D diffusion. Okay. And just like we did in the 1D case, you know, we're going to take this equation and we're going to apply it at all the nodes in our grid. Okay. In other words, we're going to go around the grid and apply this at every node I comma j that we can. Okay. And this is how we're going to get our differential equation, or excuse me, all of our algebraic equations to solve in our linear system. Okay. Okay. Assuming we have the correct neighbors for it. Okay. All right. Any questions on this? How we obtain this equation here? Okay. All right. And so, you know, just by looking at this equation, you can see why we have the IJ notation, right? Because we have a lot of, you know, I minus 1, you know, j plus 1, right? And so each of these represent a different neighbor of the node. Okay. And so if we think of I comma j here as kind of the central node, then you can see here that we have a contribution from the left neighbor, okay, because it's I minus 1. You have a contribution from the right neighbor. Okay. You have a contribution from the bottom neighbor, as well as the top neighbor. Okay. Right. And so hopefully this shows you that the reason why we need the IJ comma j notation so that we can easily, you know, find out where the neighbors are. Okay. And so since this scheme here uses the values from the node itself as well as its 4 immediate neighbors, this is sometimes called a 5-point stencil. Okay. And the reason it's called that is because, if we have the node I comma j here, okay, right, we have the neighbor up top, we have the neighbor to the left, so I minus 1 comma j, with the neighbor on bottom, so I j minus 1, okay. We have the neighbor to the right, I plus 1 comma j, okay. And so together, they make this 5-point stencil. Okay. Okay. Any questions on this? Okay. All right. And so there's our finite difference equation, right? And so, if we know the I comma j coordinate of the node that we're looking at, then we can make this equation, just like that. The problem is, when they're in I comma j format, this is not actually useful for us for building our linear system of equation. Okay. So remember, the way that we build up our linear system of equations is through the unique ID numbers of the nodes. Okay. And so before we can actually use this, we need to actually use our formula from earlier to convert these I comma j coordinates into actual node numbers. Okay. Okay. All right. And so as an example, let's use the same example that we did earlier. Okay. Okay. And so I'm going to use the same grid. Okay. And so we're going to have a grid that looks like this. Let me just redraw it just so that you're not hopping back and forth in your notes. It's node 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. And so let's say that we have a grid like this, okay? And let's say, that we want to form the finite difference equation for node number 7, okay? Okay. All right, where a finite difference equation is up here, okay? And then we can go ahead and plug in stuff for that, okay? And so, for a case like this, you can just do it visually. And so we can draw our 5-point stencil. Okay, so our 5-point stencil is going to be just like that, okay? Right. And if we look at the structure of our finite difference equation, we can see that all of the neighboring nodes, they all have the same sign. Okay, so the coefficient for all of them is 1. And then our self, the I comma j node, has a coefficient of -4. Okay, and so we can form this equation by visual inspection. Okay, and so by visual inspection, we can say that our left node here is 6. Okay, plus our right node, which is 8, plus our top node, which is 11, plus our bottom node, which is 3, okay, minus 4 times phi 7, right? Because 7 is the node of interest. Okay. And our q here, let's say it's q at 3, 2, okay? And we're going to multiply by delta squared. Okay. Where this term right here, this phi 6, we can visually see that, if we're looking at node 7, we can visually see that the left neighbor for 7 is 6. Okay. Okay. We can see that visually that the right neighbor for node 7 is 8. Okay, so this is the right neighbor. Okay, so this is the top one. And of course, this is the bottom one. Okay. All right. And so for simple cases like this, you can do it visually. And of course, this is a great way to check your work, especially if you're working them through by hand. But this is not a sustainable way because you can't tell a computer to look at something visually, tell them where all the neighbors are. Okay. And so another way to do this is to use our formula. Okay. And so we know that for node 7, we know that the I comma j coordinates for node 7 are going to be 3, 2. Right? So we have we move over 3 indices or 3 places in the x direction, we move up. Or we're in the second slot of the vertical direction, so that's 3, 2. Okay. We know that the left neighbor is going to have an I minus 1 compared to the central node. Okay, so we have I minus 1, j. Okay. So if the right neighbor is going to be I plus 1, j, the top neighbor is going to be I, j plus 1. Okay. And for the bottom, it's going to be I, j minus 1. Okay. And we can use our formula here to compute what the ID numbers are. And so if we use our ID formula, remember it's j minus 1. Okay. Actually, let me go ahead and fill in what all these numbers are first. And so let's do I minus 1. So I minus 1 here is 2. J here is 2 as well. I plus 1 here is 4. J is still 2. Okay. I is 3. Our j plus 1 here is 3. Our I is 3. J minus 1 here is 1. Okay. And so if we plug those into our equation, remember we have j minus 1, and so we have 2 minus 1 multiplied by nx. And so nx here is 4 plus I, which is 2. Right? And so we have 2 minus 1 times 4, which is 4, plus 2 is 6. Right? Next, we have the right neighbor. So we have 2 minus 1 multiplied by 4 plus 4. This gives us 8. Okay. Okay. Now we have the top neighbor. And so that's 3 minus 1, which is 2. Multiplied by 8 is, or multiplied by 4 is 8. And we add 3 becomes 11. Okay. And then finally, we have the the bottom neighbor, which is j minus 1. So it's 1 minus 1 multiplied by 4 plus 3. We get 3. Okay. Right. And so, we get the exact same ID numbers using our formula, using the IJ coordinates. Okay. Okay. Any questions on this? Okay, all right, so let's now that we have now that we know how to write these equations like that, let's go ahead and talk about boundary conditions. Okay. All right, boundary conditions. And so, in 2 dimensions, we run into the same problem that we had in 1D, right? Where this finite difference equation, the one we have here, we can only apply this at the interior nodes. Okay? And by interior nodes, what I mean by that is that they have a neighbor on every side. Okay. Okay. All right. And so, but in addition to the interior nodes, we also have nodes on our boundaries where we can't apply our finite difference equation. Okay. And so for boundary nodes, we're going to have to use our boundary condition equations to get our algebraic equations for that. Okay. All right. And so, boundary conditions become a lot more complicated in 2D because of, there's just way more boundary nodes. And in reality, if you have a domain that looks like this, okay, even for a simple rectangular domain, you might have one section of the domain, maybe something like this one, okay? Okay. This section of the domain might be subject to boundary condition 1, okay? So may that be a Dirichlet value or a Neumann value. You might have a different part of the domain, which might be only very small. And so it might be, maybe something only like this, right? So here is going to be boundary condition 2, okay? You maybe have another one that encompasses this entire side, okay? This is be like boundary condition 3. Okay? And maybe you have another one that crosses over the corner like that and covers this whole side. And maybe this is boundary condition 4. Okay. Right, and so there's lots of different combinations, and you can have infinitely many more boundary conditions as well. And so you can have, we're not just limited to 4 boundary conditions here. And so we can have 5 boundary conditions, 6 boundary conditions, and they might only apply to small slivers of the domain. Okay. Okay. Right, so there's lots of different combinations, but for this class, we're going to keep it simple. And so for this class, we're going to assume that each side of the grid or each side of the domain is going to be subjected to the same boundary conditions as everything else on that side. Okay. Okay. And so, we're going to have our domain just like before. Okay. And so, instead of having boundaries that can cross over corners like before, or maybe boundary conditions that only last for just a small segment, we're going to assume that everything on one side of the domain is subject to the same boundary condition. Okay. And so, in other words, we're just going to have 4. Okay. And we're going to refer to these by their compass directions. And so the boundary condition on the left face, we'll call this the west side. Okay. On the right face, we'll call this the east side. Okay. The top one will be north, and the bottom one will be south. Okay. All right. Yeah.
So again, we're not considering boundary conditions, or we're only considering boundary conditions on the edges.
Yes. Yeah. Yeah.
So nothing like internal.
Correct. So for the internal ones, because they have neighbors on all sides, we can apply our finite difference equation to that. And so this is only for the nodes that don't have neighbors on all sides. And so we're going to need to come up with a different equation for these ones. Yeah, so that's the main reason. So if we could apply the finite difference equation to to these nodes, then we would. But the problem is, we need to have a 5-point stencil. And so we need to have neighbors on the right, on top, on bottom, which for this node, has all of those, but it doesn't have a neighbor on the left. And so we're not able to apply our finite difference equation here. And so because of that, we have to apply a boundary condition. Okay.
Thank you.
Mm-hmm. All right. Any final questions on this before we wrap it up for the week, or wrap it up for today? Sorry, so I have one more lecture this week. Okay. All right. So on Wednesday, we'll pick it up here, and so we'll talk about boundary conditions. We'll talk about how to apply them, and then the majority of Wednesday we're going to spend in MATLAB. So I'm going to walk you guys through writing your first code or your first 2D code, because it can be challenging, because there's a lot to keep in mind, especially with the ID numbers and the IJ stuff. And so, I want to make sure we do that together so that we can, we can get everyone on the same page. Okay, so thank you everyone for tuning in today. Hope everyone has a great rest of their evening, and I'll see you on Wednesday. Question. So this code covers the homework. Yeah. So what we're going to do on Wednesday is going to help you out with the 2D problems on the homework.
All righty, cool. Thanks, Dr. Tran.
Oh, yeah, the speakers are muted. Yeah. Yeah, thanks, Chris. Thanks, you too.
Thanks, Dr. John.
Thanks, guys.
That's it.
Thanks, guys.